So let me introduce our first speaker of today. But before that, good morning, everyone. This is Meyra Çağlayan from Tampere University, and I will be chairing this morning session today. So we have 4 excellent talks scheduled for today, and we will start with Mustafa Gündoğan from Institute of Physics, Humboldt University of Berlin. And Mustafa is going to talk about some exciting roadmap event experiment, starting from some ideas. And his title is Towards Space-borne Quantum Memories. So I would like to welcome everyone, and I think we can start already.
Thank you very much for the introduction and for the invitation. And it's always a nice and warm feeling to connect with my, former colleagues, friends, and mentors in the series of COVID conferences. So thank you again for the invitation. So yes, my talk is titled Towards Space-borne Quantum Memories. But I hope the title is not misleading, because I will mainly talk about some architectures where quantum memories would be useful for long-distance quantum communication. But just a couple of words as to where I'm at the moment. So I'm part of the Joint Lab Integrated Quantum Sciences, co-located between the Ferdinand Braun Institute and Humboldt University Physics Department, where I'm kind of leading the memory activities. But we have quite large portfolio of research. And then the lab is kind of recent, established by Markus Kruzig back in 2019, and I joined in April 2020. So the group has actually large history, kind of deep history in towards miniaturizing atomic physics components and laser physics or laser devices for space applications. And then it goes all the way to 2004, where people started thinking about miniaturized or robust BEC experiments for microgravity environment. And so our group is still involved in large either German or international collaborations regarding space atomic physics experiments. And I joined in 2020 to start memor activities, because in the end, in terms of experimental infrastructure, we use the same lasers, same type of atomic systems and whatnot. And so these are some of the, these are the main research lines of our group. So the group is mainly focused on developing time standards or frequency references based on several different systems, such as rubidium vapors or strontium beam clocks. Again, these are aimed to be sent to space at some point, or miniaturized hybrid optical traps for Bose-Einstein condensate experiments. And then, of course, so my field is developing quantum memories. Just for the sake of completeness, so this is quite simple, but just for the sake of completeness, I will start with what a quantum memory is, at least from an experimentalist's point of view. So if you treat your quantum memory as a black box, then what it does and what it should be doing is to store the quantum state of an input photon, and just do nothing on it, right? And then read it on demand at a later time. So you press a button, you get it out. And so here the on-demand capability is kind of important. So why is it important? Because it acts as an interface between flying qubits, right? Photons that are used for quantum communication, and matter qubits for quantum processing, or just simply for storage. So they are needed, and so these kind of memories are needed in many protocols that involve probabilistic processes. So if you get rid of some probabilistic nature in your process and to make them more deterministic, then you can use memories, basically. And yes, of course, our context is quantum communication and networking. Again, for the sake of completeness, what is quantum communications? So it's a transfer of quantum state between 2 or more parties, right? And then here the quantum state is usually encoded in different degrees of freedoms of photons, such as polarization or angular momentum, or it could be time bins, for example. You can create even time bins. But here there's a small, but actually kind of a big problem for long distance quantum communications. That is, the loss in optical fibers limits the transmission range to around only, below 1,000 kilometers, basically. So just an example. So this is the standard example that we usually give that is usually given in the community. So the attenuation of photons at telecommunication wavelengths is around 0.2 dB per kilometer. And for those who are not familiar with the units decibel, so it is roughly 5%. So that means, you have this exponential loss. So your signal decays 5% every kilometer. And then this means that if you start with a single photon source that emits 10 billion individual pulses per second, then it will take you more than 300 years to receive only one of them across 1,000 kilometers. So this basically tells you that it is, so the direct transmission across a single fiber is, practically impossible. In classical communications, we have optical repeaters that are installed every couple of, I don't know the exact number, but every some kilometers, that simply amplifies your signal. So these are basically laser amplifiers. But in quantum physics, you have the no cloning theorem that says, no, actually you can't do this. You can't arbitrarily clone a quantum state without, because in the end, any amplification would mean kind of you would collapse the state in the meantime. But then the solution came out in 1998, I think, or 7, in the form of quantum repeaters. This I will again talk in a minute. Or the other solution is by totally bypassing the optical fibers and distributing these single photons or entangled photon pairs through free space via satellites orbiting Earth, because in the end, satellite to Earth channels. So most of the time, the photons travel through empty space, right? So they are not subjected to such exponential losses. And a little, again, simple overview of quantum repeaters. So the overall idea is that, so you start with two parties, right? But here the problem was that between these two parties, so you can't directly send your photons, right? Because they are too far. So what do you do? So you divide the whole link into 2 to the n smaller segments. So for example, for n equals 1, so we have these 2 smaller segments, and then we pairwise create entanglement between these two parties, right? And then whenever both are pairwise entangled, so whenever we get this heralding signal saying that yes, we have entanglement in both parts, then what we do now is to perform what we call entanglement swapping operation between the central 2 stations. And then in the end, the result of this operation would be to project the initial entangled states into a larger entangled state between the end parties. So here, what we did is effectively create entanglement between individual segments and then extended it across the whole, initially this long distance. But then again here, so I drew these boxes, but what are they experimentally? So they can be an entangled photon pair source and the quantum memory. Because in the end, so here, when I said you need to get both individual pairs entangled, but then these are probabilistic, right? Entanglement creation is usually probabilistic, plus you have loss. So what would happen is, so you create, for example, entanglement in one link, but then you might still wait for a little bit time until the other link succeeds, right? So until you get all the segments entangled, so you have to have a way to store this entangled state, and this is why you need quantum memories here. But then again here, so again, problem after problem. So even then, the longest range land-based, like fiber-based quantum repeaters, has a predicted range of around a few thousand kilometers. So they are still short of providing a global coverage. So here I put this note, except those based on quantum error correction. So here, as you might have noticed, we don't have any error correction. So everything relies on this heralding signal. So even if you have high loss, you don't get a click. That's it. But if you get an heralding click, that means that you can still get entangled pairs with high fidelity. Whereas this other type of quantum repeaters, I mean, these I don't go into it. You need active error correction to correct for the transmission losses. So these actually can beat this few thousand kilometer limit, but they have this, I mean, they require massive technical overhead. So instead of putting these repeater stations every tens of kilometers, in the case of heralding schemes. So here, these error-corrected schemes must have the individual nodes separated by few kilometers, like 1.5 to 2 kilometers. So, I mean, if you then want to go to 10,000 kilometers, that means that you have to have thousands of intermediate nodes, which is a massive technical overhead. So, okay, so this is the little, I mean, kind of a short summary of what quantum repeaters are. And then, as I said, the other solution to this long distance communication problem is doing everything through space, right, via satellites. So this is being done. So the first ideas were around, I mean, have been around for actually almost 20 years or so, if not even older. But China actually made some spectacular experiments in the recent years. I mean, as you see from this picture, so they successfully managed to perform quantum key distribution based on entangled photon pair sources across more than 1,000 kilometers, again, from space. But here, the small problem is that the communication distance is now limited by the direct communication of the satellite, right? I mean, but for low Earth orbit, this is around 2,000 kilometers. So, and then even if you go to the geostationary orbits, high up to like 36,000 kilometers, you can still cover 1/3 of the Earth's surface. So that means that a network of satellites is likely needed for global coverage. And we are, of course, not the only ones to think about this issue. So back in, actually, these are kind of recent proposals. A couple of architectures were proposed, but these actually don't contain memories, actually. And then the first one here, the one on the left, relies on satellites operating as trusted nodes. And then what this means is that you have to trust the security of your devices. And whereas for true entanglement distribution, these devices must be untrusted, right? And then the one on the right, this relies on entanglement swapping between satellites. It doesn't contain any memories, but and then I think here, if I remember correct, so the range is also limited to below global scales. And then another proposal was made back in 2015 that involved quantum memories. So here this group actually proposed putting entangled photon pair sources on board these satellites, right? But then putting memory stations in ground. And then in this way, they actually demonstrated that, I mean, you can bypass the exponential fiber losses. This is kind of obvious. And then with this scheme, global distances could be within reach. But here, this, of course, also, I mean, has its own issues. So the weather in all ground stations has to be simultaneously good and clear, right? Because, I mean, here, so this picture is only for n equals 1. So, and you remember it was the nesting level. But I mean, if you go to longer distances, you have to increase this n to 2 or 3, basically. That means that you have to put more and more ground stations. And then for 9 ground stations, actually the simultaneous probability of having simultaneous good weather in all stations is around 10 to minus 3, which actually, yeah, makes it again very difficult for the scheme to work. And also the other thing is, so as you increase the distance between these nodes, so the path now, so because I mean this is your atmosphere, let's say the thickest part is, let's say, 10 kilometers or so, and then so each time the photons, I mean in each link you have this atmospheric loss component, right? So this is also another issue that limits the performance of this architecture. And also, and lastly, at the time, back in 2014-15, it was thought that it was really difficult. I mean, it was a fair point at the time. Putting all these memory components in space was quite difficult at the time. But, so here I give a little pause. Atomic physics in space actually made a huge leap in the recent years. So this is a news article from 2016. At the time, people were developing kind of a compact Bose-Einstein condensate setup to be sent to the ISS, and then which is this. It was sent in 2020. And actually, so this guy here, so this is our group leader, Markus Krutzig. So he was working on these experiments at NASA back those days. Anyway, so I mean, basically, the atomic physics community in the meantime had been working on making these devices suitable for space, right? So this is the message, and then all the good results. So we have in the last few years coming from space, basically. And in addition to all these space-based setups and miniaturization efforts, already for ground-based experiments, there's massive efforts ongoing towards miniaturization of these components, right? Because I mean, in the end, so if you make everything chip-based, then you can kind of scale them up and use them in the field, in oceans, on mountains, and whatnot. So there's already a big effort in miniaturizing these memory quantum optical components, including the classical parts such as lasers. So basically, so here, all these made us to rethink the global repeater scheme now with satellites. So this is the original scheme that I showed you earlier, right? So you have the quantum non-dilution detection that tells you whether you get a click or not, whether you get a photon from space or not. And if you get a click, then you direct this photon to your memory and you load it, right? And then you wait until all the memories are loaded, right? You get a click, then you load your memory. Again, the same, you load your memory. And then once all the memories are loaded, then what you do is, again, you perform it. Then you read out the photons stored in these memories via Bell state measurement. And then again, this Bell state measurement projects the state across a larger entangled state between the two end parties. So this was the original proposal. And then what we did is we said, okay, so let's take this box, the central station, and then put this in space. Because now, I mean, here, what I didn't draw is we have the atmosphere here, right? And then when the photons are traveling here, so, I mean, here the loss is small, but here you have some atmospheric loss, right? But then if you can get rid of that loss, then what happens? So this is mainly I mean, it's a kind of a simple point, but nevertheless, it has a huge effect. And then as a benchmark, so we use the entanglement distribution time, which depends on the source repetition rate and all sorts of efficiencies, source and detection and memory efficiencies, and also the channel loss, right? Average 2 photon transmission, because we have, so every satellite is connected via 2 channels. And here is the nesting levels, as I explained earlier. So if we assume if we treat the DLCZ protocol, which is one of the first protocols for quantum repeaters, and then if we assume that we can implement this in space, so no ground links, right? Only the 2 end links are, of course, I mean, in the ground, it's obvious by definition. With single mode memories, then you need to wait for around 10 to 5 seconds to create an entangled pair across 20,000 kilometers. And so if you use multi-mode memory, so that means that a memory that can simultaneously store 100 pulses before emitting the first one, then of course it will become faster, but still not so practical. So you need to wait then 1,000 seconds, which is some minutes, maybe an hour. But then here the point is that already for low Earth orbits, the satellite flyover time is few minutes. And also the other thing is that, so it is difficult to create a quantum memory that can store individual qubits that long. And then, so this is the original protocol that that involves quantum non-dilution detection and but putting the memories in ground stations. So as you see, so after some distance, so the entanglement distribution time increases linearly in the logarithmic scale, right? So that means that actually, so this shows the effect of the atmospheric loss, right? So I mean, here for short distances, which was fine, but after some point it picks up, it's kind of shoots up, and then it goes with it goes exponential. So this is now, this means that the atmospheric loss becomes dominant indeed. But then if you put everything in space, this is then what we get. So for 10,000 kilometers, you would need only like a few hundred milliseconds to communicate, not communicate, but to distribute one entangled pair, and this becomes around 1 second for the whole global scale. And then we use these parameters here. So yes, so we could see almost 3 orders of magnitude higher key rates for truly global distances. And here, this is kind of the main message of our first paper from last year. So there were a couple of other analyses, but I will skip them because this is the main thing. So the message is memories in space, in principle, I mean, it could help speeding up the entanglement distribution rate across the whole globe. So here there is a little pause. So this is a snapshot from Twitter from last year, September the 10th. So I saw Jens Eisert. So he's actually also in Berlin, Freie Universität Berlin. His group, I saw here that actually his group is developing some simulation tools for, simulating experimentally feasible quantum repeaters. And I asked him, is this talk going to be available on YouTube? And he said he doesn't know. He didn't know at the time. 1 year fast forward, then we have this paper together. So basically, after this, so we started talking. Also, the whole link. I had written him already 2 years ago or so, but we forgot. And then, it was actually initiated by Yannick Wolters, one of our collaborators. So what we did is we applied, or they did most of the calculations, of course, because they developed the whole tool, their simulation tool to space scenarios. And so this is a work that has recently been submitted, but here we focused on only 3 satellite scenarios. So instead of having these large links, so we said, okay, let's focus on something a bit simpler, but analyze it in more detail. So we looked at 2 different scenarios, and in scenario 1, so this is actually the same scenario as I showed you earlier. So we have the entangled photon pair sources, right, in the outer satellites, and the central satellite contains a quantum memory. So here the green arrows show you the photon travel paths, right? Because we send photons here, and then the blue links show you the entanglement links, right? Because so this pair creates this entangled pair creates an entanglement between the ground station and this memory, right? And then here, so this photon pair source likewise creates an entanglement between memory and the ground station. And then the second scenario we looked at is now this time, instead of having entangled photon pair source, we use a different type of quantum memory that can create entanglement kind of internally. So instead of relying on an external photon to be absorbed, so these kind of quantum memories, if you excite them, or if you kind of excite them with strong control pulses and whatnot, so they can emit a single photon which is entangled now with an internal state of this memory, so without necessarily getting an external input qubit, right? And then this way, so here this memory here, right, now sends single photon here, which is entangled on with itself, with the memory itself. So you create one entangled pair. So in the end, you have to perform 3 Bell state measurements. And then more than that, so the whole simulation tool relies on event-based. It's an event-based Monte Carlo simulation. And then the details will be published soon. So if you are really interested, keep an eye on arXiv. So it might pop up anytime soon. And then more than that, so we introduced, it was already introduced. They already introduced it in this, their software. So the memory cutoff time is, we use the memory cutoff time. So what does it mean? So here in this work, we assume the time-dependent dephasing in the memories. So what that means is, so if this is time, if this is some sort of a measure of coherence, right, it dephases in time. And so let's say, I mean, right after the absorption, so you still keep your coherence, but at some point it dephases. And so here, this idea, which was proposed kind of recently in 2018 by Stephanie Werner's group in Delft. So what this tells you to do is that wait a bit, let's say T cutoff, right? Because I mean, let's say we are looking at these memories here, right? Or the one on the right-hand side. So we are looking at this quantum memory. Sorry. I mean, just to make it simple. Yeah, actually, it doesn't matter much. So this is loaded, right? Bam. So this is loaded. And then now we wait, right? We wait until the other memories are loaded, right? So this was the idea. So we wait a bit. And then, so here, this technique tells you, so if you don't get any other entanglement creation clicks or heralding signals from the other stations, then flush the memory, reset, start over. So in this way, actually, you can get rid of some of the waiting time. So if you optimize it carefully, of course, and you can improve the performance. And then, so the last thing that we did was to optimization of the satellite positions. So this is, again, some small, some basic plots and some main message from the paper. So what we saw was that, I mean, if the outer satellites are right about the ground stations, then you have the faster key rate, higher key rate. And so this is for scenario 1, where you have photon pair sources, but for scenario 2, it actually changes. It becomes a bit worse because, I mean, here you have to make only one bus state measurement, but here you have to make like 3 bus state measurements, so that actually makes it a bit slower. And then, so this is the cutoff time. So the effect of the cutoff time. So if you don't have any cutoff time, memory cutoff time, then the range that you can achieve is around 5,000 kilometers. But if you say, so after 2 milliseconds of waiting, if I don't get any other heralding event, then I flush my memory, then actually you can increase the rate to more than 6,000 kilometers. So this is the other main message. And then here's some bonus. So this is an ongoing work, single satellite. So far, okay, so just one thing. All the architectures and proposals that I've shown until now require quantum memories with storage times of some milliseconds or maybe less than a second, right? Because I mean, that was the entanglement distribution time according to our calculations across the whole globe. Fine. But what happens if you have a quantum memory that can store lights or qubits for hours, right? I mean, just a hypothetical question. Actually, some materials such as europium doped yttrium orthosilicate, I mean, it's actually the europium ions that do the job here. They have exceptionally high coherence times, so up to 6 hours of. So this is 6 hours of T2, and this is was demonstrated back in 2015, and towards the end of last year, 1 hour of optical storage time was shown to be doable. But here, I mean, this experiment was not done with single at the single photon level. This is another issue, another difficulty. So what happens? So if you have quite a high memory capacity in terms of storage time and multimode capacity, then you can simply create an entangled photon pair source right here and send one pair here, and then store the other pair on board the satellite, and then just physically move around the globe, and then read out the other memory, right? That stored all these train of pulses and send them to ground, basically. I mean, it is this simple, actually. So what we are currently doing is we are calculating the achievable key rates with certain memory parameters for different QKD protocols, be it decoy states or single photon pulses or entangled photon pairs. And from here, we are trying to extract the required memory capacities. And then, so it seems like one needs to have, I mean, again, this depends on the specific protocol, one needs to have really high memory capacity, like maybe a few 100,000 to million modes. So this was not, I mean, proposed first by us, so it was already an idea that was put forward by Sarah Wittig back in 2017, and then now we are actually also in contact with her and improving on these ideas. So the experimental ideas and activities. So because I mean, as I said, we are an experimental group, right? So I mean, I have, I think, only a minute left, which is, I think, fine at the moment. So we are building a Bose-Einstein condensate or a quantum memory based on a Bose-Einstein condensate in our labs here. Again, so the setup is quite similar to the one sent to the ISS, and we are also taking full advantage of our affiliation and our presence in the Fagran-Brown Institute, because we can use all these miniaturized lasers, right? So I mean, here, for example, this little board contains all the lasers, but I mean, usually if you buy them from, I mean, experimental Snowbit from Toptica or whatnot, so the whole table would be full of optical components, right? So, but instead, so this is the BC setup instead of filling the whole room. And also we have a joint project ongoing with Yannick Worters on developing portable warm vapor memories. So here I need to go a step back and to show you something else. So this is one of the papers works that was done in our group last year. So I mean, as you look at the scale. So this is only 6.5 centimeters. So from here to here, and as for, just for scaling purposes, here you have a coin. And so this is a vapor cell. So instead of cooling the atoms, then you can also do such memory experiments with warm vapors. So this little thingy here, actually it contains the rubidium atoms, right? And then we have all the mirrors and isolators, and then the laser comes through a fiber here. Again, but it can be a miniaturized centimeter long laser that is developed at FPH, this institute. So that means that, I mean, you can pack everything on a 10 by 10 centimeter module. So this is a module that is used for frequency as a frequency reference. But I mean, if you add some modulators or frequency spectral filters, then I mean the same setup can be used as a memory in the end, right? And then this is what we are trying to do. And so this is an ongoing work. This is a recent photo from our lab at the physics department at Humboldt. So we are building a compact, like really small, portable, cesium-based warm vapor memory. And then on top of that, we have a couple of other projects where we use quantum optical or atomic physics or memory techniques for sensing, like velocimeter. Like we are now starting a project on velocimeter project, yes. And then we also have another project on magnetometers. And then, yes, so the summary and conclusions. So our main motivation to start this work is that, I mean, we realized that reaching global distances is really difficult even with quantum repeaters, land-based quantum repeaters. And plus, as I showed you earlier, atomic physics experiments in space are now becoming a possibility, right? And then, like, realizing two made us actually, propose memories in space. And also there's this paper which appeared more or less around the same time as ours. I also suggest you to go and look at it. And so here the message is memories are really useful for untrusted global space networks. And of course, so this work is made possible with, I mean, it was done in this nice, beautiful group. And we have fantastic collaborators across the whole world. And I thank you, and I hope I'm not too bad with the time, but yeah, thank you.
Yeah, you're good. Thank you very much, Mustafa, for this very nice talk. I really enjoyed it. We have 2 questions indeed on the chat, and I will read them through so that everybody can hear about it. Mm-hmm. The first one is, if I use a different protocol, such as different Lie algebra, something like nonlinear Kerr media in a time-based protocol, etc. At the repeater station, then the protocol between Alice and Bob, will mm-hmm. Alice and Bob ever realize their state is being Gaussian cloned? That is the first part of the question. And it continues, I know people exploit multi-photon noise of single photon sources. Are you aware of other noise that can be exploited in this manner?
Yeah, so, I mean, what I presented was kind of a simplistic picture, right? So, I mean, for this kind of QKD protocols, what you do is, so you don't use all the photons for communication per se. So you also use some portion of the pulse of trains or these single photon trains to calculate what is called QBER, quantum bit error rate. And then you always monitor this quantum bit error rate. And then depending on the protocol, or not necessarily on the protocol, but depending on the security proofs or security assumptions you started with, so there are always some limits. So I think the usual limit that is widely accepted in the community is around 11%. So if your quantum bit error rate is below 11%, then you immediately stop the transmission because that is beyond the tolerable noise level. So I mean noise. So here in this case, it could be a third party intercepting your messages. So this is the answer I can give. And also for the I'm not sure if this will be an answer, but just a second. If I read the question again, like a non-linear Kerr-median a time-based protocol. So I mean, I didn't get what really this means, but there were also some recent protocols where they proposed to use nonlinear media as a storage medium, for example, but from an experimentalist point of view, so any incoherent click on the detector is a noise. So as an experimentalist, I wouldn't know where this is coming from, right? So I mean, if I look at my single photon detectors in the ground station, so if I get an incoherent click, I wouldn't know if this is coming from the memory from the station, from space, right? Or I don't know if that's a click from some scattering from the clouds. Because I mean, as long as it kills my visibility, it is a noise. So this, I don't know. I mean, maybe there's some other way to exploit different types of noises, but from an experimentalist point of view, as long as it kills your visibility in the Bell state measurement, because I mean, it's an interference experiment, then it's an incoherent click. So it could also be the dark count of the detector because there is no way of discerning the source, at least from this simple point of view. But there are limits to your QBER, quantum bit error rate, depending on the safety or security proofs you are using. This is the answer I can give, but I hope
it covers it. Yeah, I think it covers everything.
Okay, yeah, thank you.
And another one asks about, can you compare LEO and geosynchronous satellites advantages and disadvantages?
Yes, so I can tell you a few qualitative remarks, let's say. I can give some qualitative remarks. So if you go to the geostationary orbit, then the divergence becomes really important, because I mean, if I try to do it here, I mean, this is the, oops, sorry. Yes, or yeah, I do it here. So this is the ground, right? This is your satellite. So I mean, you can't simply focus the beam, right? Collimate the beam perfectly, but there's always some divergence, and this is the main source of loss, right? And then this comes from Gaussian optics. I mean, nothing more. It diverges simply. And if you go to geostationary orbit, this divergence, I mean, now your beam becomes so large in the ground station, right? Because I mean, it is now coming from all the way from 30,000 kilometers instead of just a few hundred kilometers, then your loss becomes huge. And I mean, you can optimize it. So maybe you would then need to use larger telescopes and ground stations, but there's one big advantage of using or being in geostationary orbit, and that is then you will be in contact with the ground station all the time, right? Because I mean, with lowered orbits, so you fly over your target in a few minutes. I mean, one needs to check the exact numbers, but lower Earth orbits gives you much higher rates, basically.
For the sake of the time, I have to skip the other two questions. But Mustafa, could you go ahead on the chat and kindly?
I can type them down there.
Yeah, excellent. Thanks. Thank you.
Yeah.
So then we can move to the next speaker.
Yeah. Thanks again. Bye bye.
Thank you. Bye.